Hello. Flying futures at the same sky can make the sun rise at midnight. You might know what I mean with futures. But the sun rises at midnight seems weird, right? In real life, this doesn't make sense. But in programming, this can happen. We can face unexpected behaviors in our program, which call it bugs. Using futures means that we are dealing with concurrency in GVM. Do you remember bugs, annoying bugs that you can never reproduce, or maybe you cannot reproduce easily due to concurrency issues? If you get lucky, you would have flaky tests. At least you can see which part of your code is buggy. But imagine if this happens in production. You would spend days and nights trying to figure out why this happens. Everything seems to work correctly. Why? Why concurrency is complicated in GVM? Today, I will take you in a journey. I will talk about the difference between parallelism and concurrency, and how could we describe parallel computations in GVM, and which kind of problems that we can face. Then we can see how could we solve them. To make it more interesting, I will cover a data type built in Zio that John DeGoss yesterday covered. It's a Scala library for asynchronous and concurrent programs. First of all, it's important to distinguish the difference between concurrency and parallelism. They are quite similar, but they are different. Parallelism is the way how to use your hardware in order the capability of your hardware in order to be able to run multiple tasks simultaneously, which means you can do many things at once dependent to your hardware. On the other hand, concurrency is the ability to deal with many tasks that are executed out of order without affecting the result. So concurrency is dealing with many things at once. Nowadays, our modern computers have many CPUs which have multi-cores. For a CPU with one core for a hardware with one CPU and 4 core, we have the capability to execute 4 tasks simultaneously. Each task will be executed in a separate core. So parallelism is clear, all of them will be executed simultaneously. But concurrency, you can have concurrent programs that are executing in different cores but are running out of order, where the scheduler will decide which task to execute at which point in time. But we can say our concurrent computations are running in parallel because at any point in time they will be executed all together. You have the power of the hardware that you can use, take advantage of parallelism. But for a machine with 1 core, you cannot achieve parallelism. But you can have concurrent tasks running in a single core that interleave each others. And every time when we run your program, concurrent program, you will have different order of execution. The order of execution is non-deterministic in concurrency. So now let's see how could we describe parallel computations in GVM. The classic way is to define a thread that contains different instructions, and the thread has a single method called run. And here, in this example, we print out in the console each instruction to see how the interleaving happens. We have two tasks. When the first time we execute, we will have the first instruction running for the first task, and then the task 2 will interleave that task 1. Task 1 will be suspended, and then afterward it will resume and execute the second instruction and back to the second task. The second time you will have different order. You even might see that your second task will start executing before the first task. You cannot know which concurrent task will be running. All of this is in the power of the scheduler that will decide for this. So the execution order depends to the number of the instructions and the number of the threads. In the clean code book, I saw the equation of how could you know how many possible results that you can have in your concurrent program. The n is the number of the instructions and the t is the number of threads. So in our example, we have 2 instructions and 2 threads, so we have 6 possible results. But it's no problem. Our program doesn't depend to each other. They can execute and interleave this way. You should consider that the creation of the thread is expensive because one JVM thread maps to one operating system thread. So this will depend to your available cores in the JVM. You can see how many possible parallel computation you can have. But imagine if you have many tasks, more than the number of the cores, your JVM, it will be very, very heavy computations happening in your JVM, which is not good. So this is why we have the possibility to submit our tasks in a thread pool, which will take each task and run them in the thread pool. The thread pool, where you can decide how many threads you want to use in your JVM and how would you like to schedule them. This helps you to save the resources. So for example, you can define your executor service with which type of the thread pool that you use. Here, fixed thread pool means that you will decide you will use 2 threads in your program that will take all the tasks that you have submitted to your executor service. So even you have thousands tasks, they will be submitted, but they will be executed only by 2 threads. This will save the resources and you will benefit of concurrency. And there are different ways to choose your thread pool type. So in Scala, we describe our parallel computation in using future. So we can put our instructions and create our future. But it requires an execution context to define where would you like to execute your task and how many resources would you like to take advantage of. If you use the global execution context, you will be you can import the implicit global, but you should consider that the performance of the program will depend to your CPU. But it's okay, you can customize your execution context and without importing importing your the global execution context. And here you can use the capability of two, like you can use only two threads to run your parallel computation. Futures are composable. You can have future, pass them around functions, and future has flat map and map where you can build your program using the for comprehension syntax sugar. You should consider that futures are flying, which means once you define your value of type future, it will be executed right away. So this program will check a condition in order to execute a future, but actually the future is already running, so be careful. You can, for example, define the future directly inside that condition. You should be aware of this. And if you have a future that takes 2 seconds, more than 2 seconds, and then print out a message, and then you would like to wait for the result and take the result from this future, but you will wait only 1 second. For sure, you will have timeout exception. Oh wait, there is the future is still flying. You should consider this. Even you see timeout exception, you should consider that the future will still running. So you should be careful. If you would like to use await.result, you should use the time, like approximately, the approximation, how much time your future will take. Future are not referential transparent, which means, like here in the left screen, your program will execute sequentially. It will, one by one, it will execute the future one by one. And, but in the right-hand side, if you want to express the future in an expression and inline your code and then call them later, like I showed earlier, the future will start flying. So this program in the right screen is parallel. They will run the 3 futures in parallel. So two of these programs doesn't have the same meanings. But it's okay, you can use lazy val, so you can, lazy futures don't fly. And as Bob Marley said, no future, no fly. So let's see now how, which kind of problems that we can face in, with concurrency in GVM. Imagine we want to build a solar system, and we define the sun as a component running in a future, the Earth running in a separate future, and the moon in other future. Each of them has its own state, but every state will be computed using the other component states. So we will have a shared state that contains the sun, the moon, and Earth state. So our program will be like this. When the sun wants to change its state, it computes the sun state, which will get the current state using and compute the state using the different component state, and then at the end it updates the state. So we are dealing with mutable shared state and the devil in mutable state. Why? Because Java memory model, when we have separate computation or parallel computation, they will be executed in different core, and each core has local cache memory that will contain the state there, and the main memory is it contains the shared state, and each different program that is running in different core will load that state from the main memory in order to use it. So there is this there are operation of store operation from the local cache to the main memory, and the fetch operation from the main memory to local cache in every core. You should consider that the store operation takes more time. It's more expensive than the fetch operation. So imagine at 11:58 p.m., the sun and the moon decided to change their state at the same point in time. They will try to fetch the shared state, then will start the computation according to the state. But if the sun starts running first, the moon cannot see the change made by the sun. And also if the moon decided to try to change the state, it will not see the change made by the sun. So there is a visibility problem. And also, besides we get the state, we will update the state. There is also a synchronization problem. Even if we are able to get to fetch the correct state, during the update, both of them, they might update the state at the same point in time, and it would be a synchronization problem. And this part of the code that change the state, get it and change the state, call it, it's a critical section which lead to a race condition. So the Earth at midnight will compute its state and will fetch a wrong state, and then which lead to the sunrise at midnight. Let's see how could we solve this problem. For the visibility problem, we can use the keyword volatile before defining our variable state. And for the synchronization problem, we can use these different solutions, and we should consider that will affect the performance of the program. Because every time when there is a usage of the state, the shared state, the whole thread should wait until that change will made. And also we should consider that there is a risk of deadlock, and also you should be very, you should know what is your critical section of your program in order to use the synchronized, for example, or you want to use the logs or something. It will take more time to explain how to use this. Let's see existing solutions that make it simpler. Zio provides a solution for this. Zio is a Scala library which helps us to build synchronous, asynchronous, concurrent applications using purely functional code. How? It will Zio separate between the description and the execution, and it will deal with functional effects instead of like each side effect, like print out of the console would be an interaction with the outside world. Every effect will become functional effect. It will be wrapped in a data type, immutable data type, and will wrap that effect. For example, now, in our case, the future, it will be wrapped in an effect. It will not be flying anymore, only when we decide to execute it. So we can use I/O to model synchronous, asynchronous effects, and each I/O, when we decide to execute it and to interact with the outside world, there is a fiber. It's a data type it's a data type built on Zio that will execute the value inside the I/O. Even the main method that contains your I/O, you want to run it, it will be executed in a main fiber. And this fiber would be, you can imagine it as a lightweight thread, which will take your computation, and it uses thread pool to run your computations. And you can have many fibers running in a single thread. So it will save a lot of resources in your hardware. And you can also, when you want to define a simple I/O, you want it to run it in a separate thread, you can just use that I/O and call .fork. Now you will build an I/O that, that will be running in a different thread. And Zio is referential transparent. The program will not change its meaning if you want to inline your code. And also when you use .fork, because it's the same data type, it will return an I/O, you will have, the previous program is a sequential program, and here you will have a parallel program. Each fiber will be executed, and both of these programs have the same meaning. And there are many functions in Zio you can use. For example, you want to run effects in parallel, you can use collect all par and put your effects in a list, and many other functions like trace, and that enable you to use parallel tasks and to control them. The data type built on Zio that will help us to solve the concurrency challenges, call it STM. It gives us the ability to atomically perform our computation in our shared mutable state. And there is also more than that. We can put a condition that a condition when it will not be satisfied, this transaction will be suspended and waiting until we satisfy this condition. But today, we would like to solve the problem of how we want to get and update and write in our state without affecting the results of the running other fibers. So we will define our concurrent program, our computation, inside the transaction. And the transaction data type is STM of EA, which might fail with an E or produce the value of type A. And our mutable shared state is called, it could be defined in a TRF of A, and the A would be our state. And this we will atomically update and read from this shared state inside the transaction. Let's see how could we do this. For example, for change sun state, now it will return an STM, a transaction, that will use the transactional reference of state. The compute sun state will fetch the from the tstate using tstate.get, and then it will compute the result, and afterwards we will update the tstate for each component. And the update and the get will return another STM result. So we will have this, each of change of the state will be defined in a transaction. We will have 3 transactions that will share the tstate of type TRF. So our program would define, we will make a reference with an initial state of type state, then we will commit this transaction, and we will get our TRF and put them feed the functions change sun, moon, and earth state with that tref, and we commit them, and we use .fork to run all of them in a separate fiber. When we commit a transaction, it will become we will describe an effect that contains a transactional effect. It's like we are describing a transactional effect, and we commit it, turn it in an IO to be able to use .fork, and then we have it's like we are running 3 separate computations that are using shared state. Now, in case when we have the same, like we face the same situation that at the same point in time 2 components that are executing in parallel wants to change the states at the same point in time, STM will retry until both of the states will be computed and taken consistently, and the Earth will have the correct state. With a simple program, we face the complex challenge of concurrency. Even concurrency is tricky, but it's powerful. It makes our applications responsive, and we want to improve the user's experience. So it's okay to deal with concurrency, and it's interesting to have libraries that helps you to just focus on your business logic, like Zio. You can put only what you want to do, and then STM will take care of these challenges of concurrency, and it has a retry mechanism, and it will make sure that your shared state is consistent. So you can do it, and you can check out Zio STM in Zio repository, and you can check out my blog post. I had 2 blog posts. It's about parallelism and concurrency. And also, if you want to use futures and you face with shared state, you can use akka actor. And if you are more interested about functional effects, and you want to see the difference between fibers and future, you can check out the video of the talk by John Dugos, Upgrade Your Future. And also there are many functional Scala libraries that helps you to describe your effectful program in purely functional code, like Zio, Katz Effect, Monix. And yeah, you can just start. It's really, you can control your program, and Zio, for example, will make it possible even to test your programs with Zio environment. There are many, many interesting things that you can check out about these functional programming libraries. And thank you all for your attention. Yeah. Is there any question?
Thanks for the talk. About the transactions, is the commit point, is that being handled by some sort of spin lock, which just waits until all the answers are in and only then continues, blocks up until then?
Can you repeat again?
Yes, so at the moment that you are making sure that the transaction actually is being completed, is that being implemented by a spin lock, which just waits until all the answers are in and only then continues?
This happens inside STM. It will wait the whole transaction that to execute all together. But once you commit it, it will be like described as an effect. But it will not do that anymore after you commit it. Do you see what I mean?
I
but
understand.
When we commit each of one, it's like we have a frozen program we committed that will contains this. We update the shared mutable state and we make sure to update it correctly. But once, if for example if the sun component will change its state in different fiber, and other one will change its state at the same point in time. Both of them will not be in that critical section that uses TRF. They will not be executed at the same point in time. It will wait, because it will retry for one of the, for example, the sun, it starts running, and then the moon will wait until the sun, it wants to change the state. It will retry until take a space to the sun to execute, and then, okay, the moon now can change its state.
That's clear. Thanks.
No more questions? Thank you all. Thanks. And I want to thank the organizers for this invitation and for this opportunity.